This is Functional Programming for Pragmatists. I'm Richard Feldman. So this is a picture of two tools that I own. I have both of them, but I don't use them about as much as often as one another. In practice, what I find is that about 95% of the time when I'm doing a project around the house, just the types of projects I do, I reach for the screwdriver rather than the drill, even though the drill has like a screw bit. I can use both of them for the same thing, but only 5% of the time do I find myself reaching for the power tool. So why is that? That's a reasonable question. I asked myself this, and I mean, really the answer is it's sort of a revealed preference. It's an automatic thing. I don't really think about it. I don't sit down and be like, what are the trade-offs between these two? I just am like, I don't know, I want to tighten this screw. I pick up a screwdriver and I go tighten it. But I sort of tried to ask myself this question and try to think of specifically why is it, like what is it objectively about the screwdriver that makes me, in practice, pick it so often? So I came up with a couple of sort of objective, observable, measurable things about the screwdriver. One is that it weighs less than the power drill. Another is that it has no battery. Like I don't have to worry, oh, did I remember to charge my screwdriver? No, it works, you know. And I've had that happen with the drill. I picked it up and, oh, whoops, got to go charge it, and then I can come back and do my project. It's also smaller. It's like easier to fit into certain places. These are sort of objective things that I can just truthfully say about the screwdriver, and they're sort of advantageous for the types of projects I do at home. But there's a reason that I actually own the drill as well, which are, you know, for example, it has more torque. Like sometimes I'm screwing a wood screw into a piece of wood, and that's like a lot of effort to do by hand, whereas the fact the power drill has adjustable torque, I can just crank it up and then boom, no problem. It also has higher RPM, so if I'm doing a bunch of screws, the fact that each one of them goes in faster is advantageous. Also, the fact that there's just like less twisting, it's sort of less exertion because I don't have to apply as much force from my arm, I can just, you know, squeeze the trigger and that's it. But the thing is, usually I'm doing projects like this. Like I'm just like, okay, I got a little screw here that needs a little bit of adjusting, stick the screwdriver in, twist it, no problem. So I could use the power drill for this, but it's kind of awkward. It's just not as nice of an experience for me. Sometimes it's kind of like the size gets in the way. I don't really want a lot of torque. I'm more worried about stripping this screw than I am about having to exert less force on it. It's just the trade-offs just don't make sense for the types of projects that I do. So I spend 95% of the time reaching for the screwdriver, even though I have both in my toolbox. Similarly, I find myself in my career, like at work over the past decade, like 95% of the time, I find myself reaching for functional programming over imperative programming, even though I sort of have both in my toolbox. The decade before that, I did exclusively imperative programming. So I know how to do both, but at work at least, in practice, I just overwhelmingly find myself with the types of projects I do as a web developer reaching for functional programming. And again, I might ask myself, why? I mean, yes, again, it's sort of an ingrained thing. I'm just like, I don't know, that just seems like it'll be nicer, but I want to try and get more specific about that because I sort of self-identify as a pragmatist. I think about things objectively. I want to try and be more specific about why I'm choosing functional programming. Because I'll be honest, like usually when I hear people explain like, hey, here's why functional programming is awesome, here's why you should check it out, it's a lot of like pretty subjective, debatable things. Like people say like, oh, it's simpler, or it's more elegant, or like it lets me something reason about something. These are all sort of in the eye of the beholder. Like depending on who you ask, one thing is simpler than another. People can make arguments about which way. Something is more elegant than another. It lets you reason about things. These are not things I can measure. I can't get out my reason about-ometer and say like, oh yes, this language is more reason about-y than the other one. Whereas these things that I said about the screwdriver, yeah, I can put it on a scale and say it weighs less than this one. I can observe that it has no battery. I can like measure it and see that it's smaller than the other one, it has less volume. So today, I want to talk about functional programming using specific objective trade-offs. Not my feelings about it, not about what I perceive to be true about it, but just things where it's like we can all agree, this is not up for debate, this is just a fact about using this particular technique. So that's what I mean by functional programming for pragmatists. Let's dive into it. So the outline of the talk, we're going to talk about first sort of the scope of like what's in scope for this talk and what's out of scope. I'm going to talk about performance implications of functional programming, again, getting specific things about development, and finally talking about sort of the ecosystem implications of all this. So let's start with scope. So in order to define the scope of this talk, I have to answer the usual question, which is, what is functional programming? And depending on who you ask, you might get a different answer. So let me just start by giving you my answer. So to me, functional programming style means that we're going to avoid mutation, and we're going to avoid side effects. I'll define what I mean by side effects later. So in this sense, the functional programming style can be done in any language that supports procedures. You don't have to use a functional programming language. You can do this style in lots of languages. Functional programming languages, I would say, is a language that primarily encourages the use of the functional style as sort of the primary way of doing things. It's not just supported, but it's the main way. That's what the standard library encourages. That's what the ecosystem encourages. That's just the way things are done in that language. It may still support mutation and side effects, but those are sort of off to the side, and it's sort of discouraged to use them. You're supposed to only reach for them like as a last resort. Now, a pure functional programming language, on the other hand, is a language that basically supports only pure functions. And to be fair, most of these pure functional programming languages have some sort of escape hatch, which is beyond discouraged. It's like if you use this and it wasn't a complete emergency, people are like, what are you doing? So there may be like FFI, like, Haskell supports C FFI, but Haskell, most people would agree, is a pure functional programming language because by default, every single function in that language is a pure function. And again, I'll define what I mean by pure function momentarily. Okay, so in scope for this talk, I'm going to focus on things like immutability, pure functions, and functional languages. I'm not going to talk about things that you often find with functional programming languages, but which aren't sort of unique to them, that are not exclusively found in functional programming languages, such as pattern matching, polymorphism, type checking. Now granted, you can find immutability in other languages than functional programming languages, and it's not sort of like that immutability is tied to functional programming, but rather that it's sort of like these are the bare minimum requirements. So when I'm talking about functional programming, I'm just going to talk about these things: immutability, pure functions, and actual functional languages. Okay, so that's the scope of the talk. Let's dive into performance. So when we talk about performance, we're going to sort of break this down into a couple of different categories. So one is caching, another is precomputing, another is parallelizing. These are areas where functional programming has advantages, and I'm going to also talk about some of the disadvantages, some of the drawbacks of using a functional style when it comes to performance. Okay, so I mentioned earlier this term pure function. Let me define that real quick. So a pure function is a function where when you give it the same arguments, it's definitely going to give you the same return value no matter what. When I say no matter what, I mean basically like unless it like runs out of memory or something like that. I mean, these are still computers. There are sort of like exceptions there, but assuming nothing sort of catastrophically unusual happens, no gamma rays, you give it the same arguments, it's going to give you the same return value guaranteed. Also, a pure function has no side effects. So when you call it, when you run that function, it's not going to modify the outside world. All it's going to do is return that value, and the only thing that it's going to look at are the arguments, or maybe like some global immutable constants. So pure functions are basically lookup tables. Shout out to Chris Jenkins, who gave a talk earlier today. He's the one I heard this from. But basically, this is, I think, a great way to think about, do you have a pure function or not? So to give an example of this, let's say I have a function called string length, and you give it a string, and it returns the length of that string. So here's a little like table of, we could sort of map, if I call it with this argument, like the string hi, it returns 2 because there's 2 letters in it. If I say GOTO, it returns 4. If I say Copenhagen, it returns 10. So I've written this out like a table, and if I wanted to, I could actually replace the string length function with an actual lookup table. Like I could just say the key is this string, and then the value associated with this key is this number. And these would basically be equivalent ways to solve the same problem. I could just say, like, rather than calling a function, I could be like, oh, string length is a table, and I just go look up at this particular key, what's the value? And those will do the same thing. So this is the way to tell if a function is pure. Could you replace the entire body of the function with one big lookup table access? If that sounds fine to you, great, you've got a pure function. If that sounds like, wait, well, no, that wouldn't do this thing, then it's not a pure function. If there's any, well, not a pure function. It's got to be, you could replace the entire body of that function with a lookup table, maybe a gigantically huge lookup table, ridiculously huge lookup table that you would never actually write in practice, hence why we have functions, but it's got to be replaceable by a lookup table if you want it to be a pure function. That's how you can tell. Okay, this has a very important implication for caching, because one of the things we do in caching is we use lookup tables. So memoization is the term for when you want to avoid running or rerunning a costly function over and over. And the way that you do it is you basically say, whenever you're going to call this function, after it's done returning, store its return value in a lookup table that is keyed on the arguments that you gave it. And then basically you can say, okay, well, the next time I would call that function, I can look and see if I have those arguments in that lookup table. And if I do, well, I don't need to bother calling the function. I'll just return the stored answer. And now I can save redoing all that costly work that was needed to compute that answer. This is a caching strategy. Pure functions are safely memoizable by definition. As we said a second ago, they're basically lookup tables already, semantically. The only difference is sort of like what they do at runtime. And so if you have a really complicated function where like making out the entire lookup table for that would take like gigabytes of memory, makes more sense to use a pure function. But because it is a pure function, you know for sure that it's memoizable. So if it is really computationally expensive to compute that answer, potentially not a problem. If you're worried about running it multiple times and having to pay that cost over and over, you can memorize it if it's a pure function. Now, a problem you can run into when doing this in like an imperative language is you can say, well, this is a pure function and it's pretty complicated, but maybe at some point along the line it calls a function that at the time you wrote it was pure, but then later on that other function stops being pure. It starts picking up a side effect or something. Now you no longer have a pure function. It's no longer safely memoizable by definition. Memoizing it might still work sometimes, but other times it might not, depending on what the side effect is and depending on like how important it is. You kind of don't know. So this is something to watch out for, and this is something we're going to talk about a couple of times in the talk, is like, if you're relying on the guarantees of pure functions, you got to make sure that, that they're staying pure even as the program changes over time. Of course, this is one of the draws of pure functional languages, is that you can rely on this always. You don't really have to worry about like, oh, is it going to secretly stop being pure? Nope, it's pure. That's all we're working with here. Precomputing is sort of like you can think of it as like an even more aggressive version of this optimization, where instead of doing it on repeat calls of the function, we can actually do it ahead of time. Anytime we're calling a pure function where all the arguments are known at build time, like they're all constants or they're all pure function calls on constants, we can just precompute that entire value. So an example of this is like if I call string length on the static string Copenhagen, we don't need to run the program to tell the answer. We can just do this at build time. Like an optimizing compiler can just turn this, into the answer by using techniques like constant propagation, inlining, constant folding, and just be like, the answer here is 10. And then that's just what gets compiled into your program. This is a very simple function, but you can imagine if you have a really complicated set of functions and it's potentially computationally expensive, in some cases when you're calling those with static constants, it's pretty nice to be able to inline those down into just, the actual answer and not even have to run it once and memoize it. Now, of course, if you're doing this based on a variable, it all kind of depends on is that variable resolvable in the same way at compile time. Like if conference name here is a function argument, yeah, maybe that's not going to work unless that function's only getting called, with static arguments. But this is an optimization that some of the time can happen, and when it can happen, it's basically a really nice performance optimization. Okay. But really, I mean, the thing that people talk about when they talk about functional programming and performance is parallelization. So if I call this function users.map, passing it format phone number, so this is a higher order function that is a function that takes another function as an argument, what the map function will do is it will iterate through all these users. So let's say we've got user 1, 2, 3, 4, 5, and say it's a really long list of users. And what it's going to do is it's going to create a new list, and the way it's going to create that new list is it's going to look at each individual element in this list, call that format phone number function on it, and then that's going to tell it how to get back the new user that's going to be in the resulting list. So user 1 gets format phone number called on it. That returns new user 1, user 2, new user 2, et cetera, et cetera. So one of the nice things about something like this is that, about a map function like this, is if you've got a super long list, you might be running it and finding out, this is kind of slow. It's kind of too slow. How can we speed this thing up and make it run faster? And a common answer is we can parallelize it. So when you run this in parallel, it's basically saying, I'm going to take this function that you gave me, and I'm going to run it on core number 1 on user 1, and core number 2 on user 2, and core number 3 on user 3. So you can do, up to like 8, 16, maybe even more of these users at a time by using all the CPU's cores that you've got in your machine. Now, whether or not this is safe to do, once again, you get a sort of different answer depending on whether or not this is a pure function. So parallel function calls may be run in any order. Like the CPUs might potentially do this, like, oh, this one's like, oh, I'm busy. Hang on, no, I'm free. I can run one over here. They can run in potentially any order. And one of the nice things about pure functions is that they are sort of thread safe by definition. Like the definition of a pure function is, means that it's only looking at its arguments, and that it's only going to return a value, which means that it doesn't really care what other CPUs are doing or in what order they're run. It's always going to give you the same answer, completely independent of what else is going on in the system. So this means that sort of like in a pure functional programming language, thread safety is just not a concern. If you want to replace map with map parallel, you just can. There's nothing to think about. It's just like, yes, I can do that. Does that seem like a good idea? Okay, well, I'll just do it. Similarly, data races, which is basically where you have multiple threads trying to mutate the same thing at the same time and potentially causing certain really nasty race conditions, those can only happen when mutation happens. So this is, again, not something that is exclusive to functional programming. Like you can write a pure function, in any programming language, like I said earlier, and data races can be ruled out in other ways than just using pure functions. Like for example, Rust famously has a borrow checker that eliminates data races by giving you compile errors if you would be using mutation in a certain way. But the point is that this is one of the nice things about functional programming is that there's just nothing to think about here. You don't have to use a particular language feature. You don't have to think about thread safety. It just works. Okay, so those are some nice things about performance in terms of functional programming, but there are some drawbacks too. The most obvious drawback is just that usually, most algorithms, in-place mutation is usually the fastest way to do the thing. The alternative to that is like if you want, we used that list.map example earlier. When you're mapping over a list, you're creating a whole new list by default. It's not doing in-place mutation, and in-place mutation is usually a faster way to do something if that works for the algorithm that you're using. Also, managed effects can have non-zero overhead. So this is another new term. Let me explain what I mean briefly by managed effects and how they're different from side effects. So side effects, an example of side effects is promises in JavaScript. Managed effects would be sort of an alternative way to do the same thing as promises. So here's some sample JavaScript code saying promise1 equals fetch and then giving it a URL. So this is the HTTP fetch API. It's basically going to run an HTTP request to that URL and then give you back whatever whatever comes back from that server. Promise2 is again calling fetch on a different URL, and then it's calling .then and passing in some callback. So both of these are examples of fetch, and then also fetch.then are returning a promise, which is basically JavaScript's asynchronous abstraction. So this is what's called a side effect, though, because even though there is that promise wrapper around it, right when I call the fetch function, it immediately does the HTTP request. Like as soon as I execute that, it is immediately going to run the request. Now in contrast, the managed effects version, this over here is Elm code. When I call fetch passing this URL in Elm, it's going to give me back a task rather than a promise. But as you can see from these two examples, like task 2 is fetch URL and then piped and then callback, structurally, these are basically the same thing. Either we're saying like fetch or we're saying fetch and then do this callback. The only difference here is that it's promise versus task, or the only like significant difference. The difference there is that whereas the promise is running the HTTP request right when you create it, instead the task is not. The task is just a description of what you want to be done later. So if I called fetch 100 times in JavaScript, it's going to run 100 HTTP requests right away. If I call fetch 100 times in Elm, nothing happens. It's 0 times 100. Just 0 things happen. It's just building up a description of what I want to be done. So then the question becomes, okay, but like surely eventually we want to actually do the HTTP request, so how does that happen? And basically the answer is that what you give to main in Elm, like the main start of the program, is essentially like one of these chained together tasks. And then main says, okay, I know what to do. And then when your program starts up, main says, I've got this big long list of tasks. Now I'm going to evaluate it. So the key is really just, are we building up a description and then giving that to main to run? Or are we actually, as soon as we call the fetch function, immediately running the effect? And that is the difference between lookup table versus not. If you wanted to, you could take all of these pure functions that you've got in the entire language, and you could replace them with lookup tables. It's just the thing that would be coming out of the lookup table is a task. That's the difference. Okay. Now I said managed effects can have non-zero overhead. What I mean by this is basically that in JavaScript, you don't necessarily have to use a promise-based API. It's quite common to use a promise-based API, but it's not required. There are APIs that don't have that promise wrapper around things that gives you this sort of abstraction for asynchronous effects. But in a pure language, you do need something like that. You have to have some sort of wrapper because you have to be able to store this thing and say like, this is what I'm actually returning. You can't just like run it and then it's done with no wrapper. That can have non-zero overhead, but worth noting that compiler optimizations can reduce it and potentially get it all the way down to zero overhead by using things like inlining and whatnot. But by default, in most languages, there is some overhead there. It's usually pretty minimal, but it's there. One more note about performance. There's a lot more to this topic of like sort of things that are normally true but don't necessarily have to be true depending on the language. I gave a whole talk about this at Strangeloop about a month ago called Outperforming Imperative with Pure Functional Languages. If you want to learn more about that topic, I recommend that talk. Okay, so that's performance. Let's talk about development again through this same lens of like, not my opinion, but just like things that we can observe that are true about the characteristics of pure functions and things like that. And this to me is the good part. Performance is cool, but development is the part that I really enjoy about functional programming. So let's start off by sort of outlining the things we're going to talk about. We're going to talk about testing, revising, debugging, and of course, same as before, some drawbacks to the pure functional style when it comes to development. So, woo! Sorry, I didn't mean to scare everyone. I know it's like a month past Halloween, but let's just talk about something that nobody likes to talk about within the topic of testing, which is flaky tests. So flaky tests are no fun. They're difficult to debug. They're a pain. But they do have a sort of known cause, which is either a race condition or an effect. Like something didn't happen the same way that it used to, or it happened in a different order than it's used to happening, and this is what caused the test to momentarily flake. Well, one of the nice things about pure functional programming, or even just functional programming in general, is that you're trying to minimize side effects and sort of not use that as a default strategy unless you really need to. That has the consequence that you're minimizing effects in general. You're sort of doing things in a less effectful way, which means that you're having fewer flaky tests. And in fact, you can take this all the way to using a pure functional language where, like for example, I work at a company called No Red Ink, and anecdotally, we've been using Elm in production since about 2015, so yeah, 6 years now. And at this point, we have about 500,000 lines of Elm code running in production, and of those, like hundreds of thousands of lines of code worth of Elm tests. And since 2015, between then and the present day, the total number of flakes we've ever had with our Elm tests is 0. It's never happened. We've never had a single flaky Elm test ever. And this is not surprising because they can't. They're all pure functions. There's nothing that can possibly flake. We run them over and over and over, and they just give them the same arguments, and they give the same answer, and that's it. There's just no opportunity for them to flake. We also have a big Ruby code base. Slightly different story in terms of flakes. Not going to go there. But this has just been a really nice experience for us. If you're not familiar with Elm, it's elmlang.org. It's a delightful language for reliable web applications. I would subjectively agree with that. And this is like one of the aspects of that delight is just like tests that don't flake. Now, granted, I've been talking about this in terms of minimizing effects, but there is another piece of this story, which is that if we don't have any effects, there's no mocking needed. Okay, that's another benefit. Great. There's no flaking. Also great. But what if you actually do have effects? Like what if you have these managed effects like we were talking about earlier, which definitely does happen. Basically, instead of doing mocking, you can also test effects by doing essentially simulation. This is basically, you've got your big built-up task, and you say, okay, I'm going to run this thing, but I'm going to sort of simulate at each chain of the task. Well, I'm going to assume that this first task in the chain gets these things, and then the second one gets these things, and the third one gets these things, and the first one's going to return this when it gets those, and it's going to return this when it gets those, and so on and so forth. So it sort of serves the same purpose as mocking. I personally find it more ergonomic, but that's subjective, so it's out of scope for this talk. But the point is, you can still do it, and you're still not going to get any flakes. So some examples of this, like in practice in Elm's, like HTML tests and also Elm program tests. These are ways that we can sort of like test the entire program, including all the effects in it, without ever having any possibility of flakes and using simulation instead of mocking. Okay, revising code. So let's say I write this line of code. I'm calling format phone number, giving it a user, and I'm taking the return value of that and calling it phone. So this is just going to format the user's phone number in some sort of standard way in terms of spaces and whatnot. Then I'm also going to see if the user is valid. Like maybe someone's filling out a form. I want to see if what they filled out is valid. So I'm calling check valid on that same user value. Now let's say that I were to switch these around. Do nothing else, just swap the order of them. Does my code still work? I mean, this is a thing that I like to do sometimes. I'll realize that like, hey, maybe if I call these in another order, it's the code's going to read a little bit nicer. I like to rearrange things. Does the code still work after I've rearranged it? Well, potentially not. Potentially, depending on the language, this might cause a bug. Why might this cause a bug? Well, one reason is that maybe check valid mutates user. It doesn't just check that it's valid, but for some reason, the way that whoever implemented it, it modifies something about the user, and maybe it modifies the phone number, such that when I call format phone num later, it's actually calling it on a different phone number than before. And because I'm now calling them in this order, that mutation affects the format phone number call. You can avoid this in ways other than functional programming, though. Like Rust, for example, has mutation annotations. So you can actually see in your function's type whether or not it's allowed to mutate the arguments that you're giving it. I've been spending a lot of my time outside of work using Rust. It's probably my favorite imperative language at this point. And it's definitely true that this like sort of cuts down on these things. Although, worth noting, I've definitely still bitten myself with this. Usually it's not an example this trivial, but I mean, it's a presentation, so I'm kind of having to shrink it down. Usually what will happen is I have some like big chunks of code that I'm rearranging in various ways. And with Rust, sometimes I'll rearrange that and I'll get an error saying like, hey, this thing's mutating this thing, you can't do that. Whoops, and then I'll revert it. But sometimes it still works because that thing happened to have mutation permissions already, and now it's mutating in the wrong order, and it doesn't work anymore. On the other hand, I don't actually have this happen to me in Elm. I just rearrange stuff as much as I want. And in fact, in Elm, it's actually true that you don't need to have an ordering to your assignments. You can just rearrange them however you want, and the compiler is always going to just say, okay, those are all equivalent. Another thing that can happen is, even if I have a language with mutation annotations, What if it's not that it's mutating this user value, but rather that it's going completely outside my system and writing to a database? And what if, for some reason, this second function is reading from that database? Now the order matters again. And again, reordering these things can potentially cause them to break. So this is another way that we can get a bug. Even though there's no mutation involved, it's still just like that side effect of writing to a database and reading from that database means that the order matters. But again, pure functions just don't rely on call order. You can just reorder your assignments, and like I said, in Elm, you're just allowed to. The compiler does not care how you order your assignments. They all do the same thing. So whether I write it like this or I write it like this, exactly the same. And I've gotten used to this, like in pure languages, that I can just restructure my code kind of however I want without really thinking about it. And it definitely has bitten me when I got back to Rust. And sometimes I've ended up making refactors. I'm like, this is better now, and it doesn't work anymore. I'm like, all right, I'll put it back the old way. So this is again like something that's depending on how much revising you like to do, how much refactoring you like to do of your code. This is just something that's just objectively true about pure functions, that you can reorder them. Okay, and finally we come to debugging, which for me is sort of like maybe the biggest benefit here. So I was told earlier on in my career that global mutable variables are bad. Just don't use them. Like, they're there, but just don't use them. At this point, I think I've years later, I don't want to say that anymore. I think that was maybe reasonable advice to my former self, but I think it's too broad. I would like to be more specific about like what is the downside of global mutable variables, because there are some times when they're legitimately the right choice. The problem with global variables, or the downside of them, is that they create implicit dependencies. So let me explain what I mean by that. Let's say I have this function. It's count messages. It takes a user and returns an integer. So let's say that the input to that function is just the user. And I think we can also say that the output to that function is an int. At least as far as we know. Like, this is like a C header kind of style pseudocode. We don't really know what the body of this function is, but just looking at this declaration, we can say that like it's got one input and one output. So if the output value is wrong, like the value that it's returning is wrong, like which functions might be to blame? Who is the potential culprit here? It's like, well, it's count messages. So if I want to debug this, I'm just going to step through the count messages function and just see at what point it's causing the answer to be wrong there. Okay, but now let's say I introduce a global. So a global mutable variable. This is also an integer. Well, now there's sort of an implicit potential input to this function, which is this global. Like, if I call count messages multiple times, and I give it the same user, it still might give me a different answer because it might be reading from this global. Now again, we can't see the body of this function here. We're just looking at the declaration. So just based on the declaration, the fact that I've added this global to my program means that when I'm debugging, I now have one more input to consider here. I also have one more output, because when count messages runs, it can also mutate that global, and other functions might be relying on that. So I've increased my inputs and outputs to this function by one just by adding this global, at least as far as like looking at the declaration. If I want to see whether it depends on it, I now need to like go into the body and actually see, does it actually reference the global or not? And this is not just for this function, it's for every single function in my code base, which is potentially a lot of them. And if I add a second global, it's again multiplied by all the functions in my code base, another input, another output. So this is what I mean about like implicit dependencies. If this value is wrong, like which function might be to blame? I mean, could be any of them. Could be any function in my entire program that like changed that global. So how do I go about debugging this thing? I mean, I kind of just need to like step through all the function calls in my program. Or if I have some IDE, maybe it can tell me like, okay, here's the only functions that reference this global, and then I can narrow it down that way. But I mean, the amount of functions that can potentially be affected by this thing or potentially affect this thing is just all of them. So I wouldn't say that global mutable variables are bad. I would say, though, that they create implicit dependencies. Similarly, I also would not say the side effects are bad, but I would say that they introduce implicit dependencies. Because they do, in basically the same way that global variables do. So like, let's say that I have this count messages function, and I know for some reason that it's a pure function. If this value is wrong, which function might be to blame? Just count messages, no problem. But again, if it has side effects, which functions might be to blame? Well, I mean, what if it's like reading from a database? What if it's reading from a remote server? It could be doing HTTP requests. It could be reading from some local store in memory. That's not one of its arguments. And what are outputs? I mean, it could be changing a database. It could be changing a remote server state. Like, what if I have this remote database that my program talks to, and that state is wrong somehow? I'm like, running my program. I'm like, wait, why does that column have that value? Which function in my program might be to blame? Could be any of them. If they all could do side effects, that's one of the many side effects they could potentially do. So again, how do I debug that? I have to potentially step through as many as all the function calls in my database. as opposed to being able, like if I know that this function is pure, I'm like, yeah, I don't have to worry about that. Like if I know somehow that, whether it's a pure language or because I've been following a pure functional style and I'm confident that this is a pure function, I'm like, yeah, I may not know exactly which function is to blame, but I know it's not this one. I can rule this one out right away just by looking at the declaration. I don't even need to potentially like step into the body of the function or run any IDE commands to try and figure out if it references things or not. And in the case of globals, maybe I could have gotten it to reference things and say like, oh, this function references these globals, but what am I going to look for if it's like accessing the database? I mean, hopefully I do all my database access through one function. Maybe I can it's a lot harder of a question to ask. The state space to search is a lot bigger. So basically, in a sort of a pure functional context, if I'm using pure functions everywhere, especially if I'm in a pure functional language, and I'm wondering how my database got changed, I can debug only functions that return wrapped effects like task. So if this returns task, then okay, maybe this is one of the functions. But now I can tell. I can immediately partition my search space for potential culprits down just way smaller, down to only the ones that actually return tasks, just because I've been following this style. So in the world where I have side effects, my search space is potentially as big as the entire program. But in a world where I'm using pure functions everywhere, the search space is just way smaller and potentially astronomically smaller, depending on how many tasks I have, like the ratio of functions that return task to functions that return not task. So this is a way of just like making me just strictly spend less time debugging just by virtue of the fact that I'm following this style. Okay, so having said that, again, there are some drawbacks here. Explicit dependencies are more verbose. Like not just the fact that I have to return task, but mutations are another really common example. Rather than being able to pass in a user and say, I'm just going to mutate this thing, if I want to follow a pure functional style, I need to not only take a user, but then return a new user that's modified version of the original. That's just more verbose than having the implicit dependency of being able to mutate it directly. Also, managed effects make functions colorful, which when I say it like that sounds like a good thing. And honestly, to me, it is a good thing overall, but there's definitely another perspective on this. Like from my perspective, I like the fact that I know that all of my functions that return tasks do effects, and if they don't return tasks, they don't do effects. But there's a downside to this, which is if you have like a deeply nested function call and you decide that you want to do an effect in that leaf node, now you have to make it return a task, and also this parent caller has to return a task, and its caller has to return a task, and so forth. That is definitely a downside. There's a whole blog post about this called "What Color Is Your Function?" that sort of talks about this downside. And it's about really wrapped effects like task and promise. It's not necessarily specific to functional programming. But if you're following a pure functional programming style and you want to get these benefits, this is one of the drawbacks that sort of comes with that territory. Okay, so that's development. Let's talk about sort of like putting all this together and the sort of ecosystem implications of the things that we're talking about here. Okay, so before I got into functional programming, I was a JavaScript programmer professionally. And I was at first doing it in an imperative style, and then at some point in my career, I found out about the functional style and sort of started writing in a functional style where I was avoiding mutation and avoiding side effects. And one of the things I learned sort of the hard way is that, as I mentioned earlier, a pure function that calls a non-pure function is no longer a pure function. It no longer gets all the benefits that we've been talking about. Found this out the hard way in some cases because I made a mistake. Like I thought I had a pure function, but I actually just didn't apply the rules correctly. I didn't, at that time, have the mnemonic of like, oh, could I replace the entire body with a lookup table? I think that would have helped me out, but didn't have it at the time. So sometimes I'd mess that up. Or sometimes I would have it be a pure function, but it's calling this other function, which calls this other function, and then that one stops being pure and I don't notice. That could also break my assumptions. Or even worse, I did call a function which calls another function which calls a function in somebody else's package, and maybe I just update my packages and there's no breaking API change there, but it turns out that something picked up a side effect and now all my stuff breaks. So this was like somewhat of a bad experience that I had. So if I had this function like count messages that we've been using before, I would have all these questions about it that I wanted to be able to answer with the pure functional, just like, oh yeah, I know the answer right away, but I couldn't necessarily always do it. So I'd ask like, okay, might this count messages function be what changed my database? Or what inputs does this thing depend on? Is it just user or is it more than that? Does this rely on call order or not? Can I rearrange it? Could this flake if I put it in a test? Can I pre-compute this? Like, do I need to run this at runtime, or like if it's expensive, can I potentially compute it up ahead? If I can't do it at compile time, can I memorize it at runtime? So if I'm rerunning it, I can potentially not have to pay that cost over and over again. And like, is this thread safe? I mean, in JavaScript, that's not so much of a concern, but like I was a Java programmer before that, so like I definitely remember thinking about these things. And again, if I'm confident that this is a pure function, I know the answers to all these things. Might it be what changed my database? Well, it doesn't return a task, so yeah, definitely not. No problem. What inputs does it depend on? Just user. Easy. What else you got? Does it rely on call order? No problem. Could it flake in a test? Absolutely not. Can I pre-compute this? Yeah, if I want to. Can I memorize this? Sure, also fine. Is it thread safe? Absolutely. So if I know it's a pure function, I know all these nice things about it. But again, in the JavaScript world, can I really be sure it's a pure function? Like, I hope it's a pure function. Like, I think it's a pure function. And most of the time when I was programming that style, and I was on a team of people who were also bought into this, most of the time we wouldn't make a mistake and it would be fine. But sometimes it wouldn't be. Sometimes we would have this like, oops, not pure anymore, and then we would get burned by one of these things. And then all these nice answers would go away, and we would have bugs. So this was my experience like doing JavaScript in the functional style, and I gotta say that one of the biggest parts about being a JavaScript programmer is installing lots of packages from NPM. And I would have this question mark around the confidence of things I was getting from NPM, because let's face it, NPM is largely written in an imperative style. Like most of the packages on there, the overwhelming majority of packages on there are not really concerned about side effects. There are definitely some functional libraries, and there are some other packages that are built on those functional libraries, and there are other packages that happen to not use side effects and things like that. But culturally, it's not really like everybody's like, you must avoid side effects. This is a pure function. You can rely on it being a pure function. I've verified that it's a pure function. I'm never going to change that. It's not really how it's done. It's a lot more loosey-goosey than that, and that's kind of how these bugs can happen. In contrast, eventually later in my career, I got into Elm, which is a pure functional programming language that compiles to JavaScript, and I started using it instead of JavaScript for my front-end programming. Elm has its own package ecosystem, package.elmlang.org, and it's 100% pure functions, guaranteed. No exceptions. There's not even like JavaScript interop allowed on there. It's just like, you can do JavaScript interop in your program, but on the package ecosystem, it's like, no, 100% Elm code, 100% pure functions, so you never have to worry about any of that stuff. It's just all the questions, all the answers to all these questions we've been talking about, it's always like, yes, it's a pure function. Not a problem. I don't have to think about that. So I have this like supreme confidence when I'm writing Elm code. I can just like refactor stuff, reorganize it however I want. Tests never flake. All these benefits, I just get them 100% of the time. And this is like sort of an unbeatable ecosystem benefit to me. Like the Elm ecosystem is like one of the biggest selling points of the language to me, even though it's by like numerically, it's much smaller than NPM, which is the biggest package repo in the world. I am much happier using this ecosystem because all of these objective properties we've been talking about hold for every single line of code in this entire ecosystem. So in JavaScript, when I'm like, I don't know about the answers to these questions, I don't know, maybe I have to like, hopefully they hold. No, in Elm, it's just, there's this complete peace of mind. It's like, yes, it's a pure function, for sure. I get all these objective benefits, for sure. There's nothing to worry about. Which means that all of these things, in practice, are just not in my brain anymore. Like when I'm writing Elm code, I'm never spending time thinking about these things. I just have all these cycles freed up to think about like what I'm trying to build. And subjectively, that's what I love about functional programming. It's all the things that I don't have to think about anymore because I'm just working in this world where all these questions just have a very immediately known answer. I just don't have to think about them. I don't have to worry about them anymore. So that's why in practice, 95% of the time I find myself reaching for the functional screwdriver, even though I'm still happy to have the other one in my toolbox. Okay, so to summarize all the things we talked about how sort of traditionally the way that people talk about functional programming is subjectively in terms of like it's simpler, it's more elegant, you can reason about things better. But the goal here of this talk is to focus on sort of the pragmatic, concrete, measurable things that are different about functional programming. The style, the languages, specific objective trade-offs, both pros and also the cons of using this style. We talked about caching, how things are sort of more innately memoizable if they're a pure function. If you're using pure functions, they're innately parallelizable. You can pre-compute them ahead of time and sort of not even need to memorize them at compile time. We talked about testing. You never have to worry about flakes. You never have to use mocks. You can use simulation for wrapped effects. We talked about revising code. You can reorder them as much as you want and not have to worry because pure functions are order independent since they only depend on their arguments. And we talked about debugging and how the sort of search space for potential problems is much, much smaller if you have functions that aren't doing side effects. And again, this part, the development, much more so than the performance, is the reason that I've come to love functional programming. And finally, we talked about ecosystems and how there is a lot of benefit to be had from using the functional programming style, but it definitely does come, at least in my experience, with occasionally getting bitten by assumptions not actually holding in practice. And sometimes that's because of the ecosystem and things that I got off of NPM or other package managers. One of the really nice things about a functional programming language, or especially a pure functional programming language, is if you have an ecosystem where these guarantees are actually enforced like they are in Elm, all these things can just go out of my brain and I just don't have to think about them. And instead, I can think about what I'm actually trying to build. And as a pragmatist, that's what I want. And again, I want to reiterate, I still want both of these in my toolbox. Like, yes, at work, I spend most of my time doing functional programming, but actually on the side, I spend most of my time doing Rust. I've been working on some really performance intensive stuff where I just really want that. I want a systems level language. And I also like Rust a lot. I'm definitely not like somebody who thinks that functional programming is the only way to do things. But again, when it comes to work, 95% of the time, I'm still choosing the screwdriver, functional programming over imperative, because of all these things. And I can say that in full confidence as a pragmatist. Thanks very much.